So thanks again for coming. This is already third meetup in H2O.ai. And right now we are really happy to welcome our friends from Booking.com who will be doing their first talk. So really thanks for coming. It's really a pleasure to have you here. The second talk will be about, I'm gonna let their talk for them. The second talk will be about using AutoML and grid search in sparkling water. So that's up to Martin Barus. So he has been working hard on this, so I'm really happy to see it done. And the third talk will be after our short break about machine learning interpretability by Martin Barus. Just a few notes, few more slides about this meetup group. We are opening meetups around all the world. Even though we are based in few cities, we are opening meetups groups really around the world. And a few notes about the company before I let the two speakers come in. The company was started in 2012. Right now we are in Series C investment. We are mostly working, we have our open source tech, Sparkling Water, H2O free. These days we are heavily working on driverless AI, which is our closed source product for automatic machine learning, including automatic feature transformations. Our mission is, probably you heard our CEO, that we want to do good. We want to make artificial intelligence accessible to everyone, so that you can start driverless, start Sparkling Water, click, and have your model available. We have around 150 employees. Most of them are based in California, Mountain View, our HQ. But we have also offices around the world. The second largest office is in Prague, here. And we have also offices in Singapore, New York, and London. And that's probably everything I wanted to say. So thanks again for coming. And I'm going to welcome Shanti here for his first talk. So if you can please come here.
Hello? Ooh, works. But does this piece of equipment work? Holy shit. Alright, hello everyone. I'm Santi. I'm joined here by Ivana. I'm a senior developer at Booking.com. Might have heard of it if you ever try to book a hotel for yourself. Let's talk facts and figures that are interesting for data scientists, so we can set a little bit of the scene for the talk. We are a company that is able to produce about 50,000 predictions a day from about 400 machine learning models, crunched from petabytes of data, tens and thousands of cores. We kind of take machine learning pretty seriously, is what I'm saying. But one of the things about it is that a machine learning model that is great just on Jupyter, in PySpark, etc. It's not something that we are very interested about, because if the machine learning model is not able to provide some value for our customers, some personalization, to make our customers' life easier, then, well, it's great, it's a great piece of maths, but it's not helping us, it's not helping our customers experience the world, which is our mission. So, let's see what the problem is here. Building models usually goes through a number of steps. First, you probably make an hypothesis, so you have something, some area that you want to attack. So you collect some features about the thing that you want to make predictions about. Then you try and assemble them in a way that makes sense, that your model may have a chance to make predictions about, and then you call train. And then leak the label. All right, try again, maybe drop this column, try again. I've expected this column to be really important, but the model is not really working on it. Let me try maybe categorize it, bucketize it, normalize it, make sure that it's in a shape that the model can, the mathematics can work on. Okay, I got a model, it looks great. it's performing like I want to. And in terms of tech stacks, usually you would go through this journey by using one of our so a data source is either some proprietary event stream or other streams that are built ad hoc with Kafka or Kafka Connects. A data scientist would then process this, usually using PySpark, but in reality we pretty much use everything under the sun, including good old bash scripts with awk. For training models, H2O is very popular. A lot of people like Wabbit, but again, pretty much everything under the sun is in active use. The iteration process usually done with Jupyter, but we have people working also on RStudio, the H2O web dashboard, or just Bash. And finally, deployment structure is usually done with another proprietary structure, though there are models that are so simple where people have decided to just write the implementation directly in Perl. So one thing that you might notice is missing here is modules. Why are we not using modules directly? That's a great question. So the thing is, this is the data scientist workflow. Once the data scientist gets to the end and it's got a model that is ready to be deployed, this is probably where they would like things to end. But that is really where the fun begins, right? Because now we need to take this model and run it tens of thousands of times per second for our customers to actually get predictions. And what does that look like? It's kind of like the same, right? So we receive a web request, we collect all of the information about the customer, we transform them, we call the model, and then we get a prediction, we customize the experience, and maybe the customer makes a booking. Great. So here's the thing. We have at the top the data science world, where our beautiful team of unicorns will take some features, then transform them, and create a model out of them. Then we have the backend developers, typically, who will try and collect the same feature, try and transform it in the same way, and then try and run a model that kind of looks like the one our unicorn, the beautiful, beautiful piece of maths that a unicorn came up with. And sometimes there's a little bit of miscommunication going on. The more things are left to manual coordination, the more room for mistakes there is. And there's really no end to how deep this rabbit hole goes. So we want to try and align these two pipelines as much as possible. So one way to do it, so there are a bunch of technologies to help with this. We have Kafka Connect, so we backenders can be like, hey data scientists, you want to do predictions, that's great. These are the numbers that you can work with. We're providing them to you, and these are authoritative, so if you work with these numbers, you'll know that we'll do the right thing once you go in production. For models, yeah, we have modules. So we know that once you create a module, then we can call the module, and we will have exactly the same model as you created it also on our servers. For feature transformations, it's an exercise left to the reader. I may just pipeline. I can't use it. Guess I'll die. Right, so what's wrong? What are Spark pipelines? Spark pipelines come with three major concepts. We've got transformers, take a data frame, transforming it into some other way, for example by bucketing it. We've got estimators that produce transforms based on some training data. And then we've got pipelines that just run each step one after the other. And you can stop, you can serialize them, you can have them on your disk, but it's kind of about it. So we kind of try to fix this, and we call the solution booking transformations. So what does it look like? You import pipeline, the classic the normal PySpark pipeline implementation, and then we have our own implementation of the various steps. They're pretty much the same. So here, for example, we have a bucketizer. We have some review scores. We know from domain knowledge that the review score, usually, I don't know, if it's less than 6, probably you don't want to stay at that hotel. I didn't say that. So maybe you apply some domain knowledge and say, okay, maybe 6, 8, and 9 are good separation points for review scores to turn it into categorical. And then, but here we have a standard scaler. So what it does is it takes a bunch of numbers and then makes them so that the average is 0, the standard deviation is 1. To do that, you need to apply an offset and then a scale. And we don't know a priori what that looks like, right? So we need to calculate that. And what you do normally is you build your pipeline out of a couple of these stages. Then you fit the pipeline over the training data, you transform the training data, you transform the validation data. What's wrong with it? Well, nothing is wrong with it, but we can do a little bit better. For example, as part of this process, we noticed that, for example, the bucketizer, while we're feeding the data, the bucketizer actually does the bucketing work. Because maybe there are further steps down the pipeline that depend on it. And then when the function returns, all of this data is, well, garbage collected, because all we get back is the pipeline model. So one thing we did is a thing we call a frame extractor that gets us appointed to that data frame that was already transformed. And that gets us a little bit more performance out. Another thing we can do is parallelize things a little bit. If you're bucketizing several columns separately, then what we're able to do is do them in a single pass, for example. But what is more interesting here is that we are actually able to take this have a custom serialization of this pipeline in a way that shows, it basically looks like this. Well, it's just a JSON document that's a bucketizer with the buckets we specified, there's a scaler, and that's the offset and scale that we learned. Then we can take these JSON files and put them on our model serving platform. And that means that now, yay, we are in kind of full parity, or at least as close as we can guarantee you to be. And that is actually what is allowing us to pump out more models, get them faster to our customers, and deliver innovation more quickly. What kind of transformations can we do? Well, the usual. We can do imputation. We can imputation, so that's fixing missing values, making buckets, encode interactions between different features, do scaling like I've shown. And now that we have the power to do more interesting transformations in a way that is scalable, we can do more interesting things like target estimators. And Ivana will tell us more about it.
Can you hear me? Yeah, you can. So, hi everyone. Thank you for joining us today. Once now we have this amazing pipeline for the feature transformations, I'm going to tell you a little bit about how we coded the target encoder. Target encoded is well known, the feature transformation. It's used, there's implementation in H2O. We did added a little bit of our own magic on top of it. So the basic idea behind it is to encode the categorical variables by looking at the relationship with the response label. Usually when we're talking about this, we're talking about the categorical variables with a lot of different levels. When you think about cities or different hotels, we have 2 million hotels, maybe we want to encode those. Really features with a lot of different levels. So two things that we looked into it by creating this feature transformation was how we can prevent the leakage and how we can deal with the sparse variable values. Talking about the leakage, when you think about it, how you build the target encoder, there's intuitively something sounds fishy. This will probably leak information to my validation data. In order to avoid that, you just need to be a bit more careful with the calculation, and so we're fitting this only on our training data, and we're calculating the out-of-fold statistics for target encoded value. To deal with the sparsity, what we did, so basically we defined inflection point that determines actually how big of a sample I'm willing to trust. So if you think about your data and you think about, let's say, the cities, there are some cities where we have only a couple of examples. So we probably don't want to calculate the target encoded value for those ones. So we define the inflection point, and then the slope determines how quickly our trust around that inflection point deteriorates. So basically, if you look at this, a lot of formulas there, it's actually just trying to find the inflection point and then fitting the sigmoid function around it to smoothen out this trust. So how do you find the inflection point and the slope? But those are basically hyperparameters. So there's no given value, given your problem, those should be tried out. What we do at Booking, we usually use the Bayesian framework for estimating the hyperparameters, but of course, any other will be fine. So how do we apply this target estimator? So using the feature transformation pipelines as Santi described before, so it's just a matter of building the target estimator object. There's a slight difference then from maybe bucketizer and or the scalar is that in this case we actually need to define the response. The fold, so basically this is just a fold column, so we know how to shuffle our data, and then the slope and the inflection point. Once this is built, and we found the optimal values for the slope and inflection point, we just need to add this target estimator object again to our frame extractor, and the magic is done. This enables us to have this powerful feature transformation in production, because syncing data scientists with developers, especially on a bit more touchy feature transformations, was historically very painful, meaning we had to redo it a couple of times. So this is skipping a lot of steps, and it's making our lives easier. So next thing I'm going to talk about is the feature importance and interpretability in tree models specifically. So just starting about interpreting a model in general, it's a very hot topic. I mean, it was always an interesting topic, but I think recently with more tools available that are making it more scalable, it's becoming more and more interesting. Also, some legal regulations are kind of making it obligatory rather than interesting. So talking about interpreting a complex model, usually we talk about the two different levels. So whether we want to interpret the global, have a global interpretability, or we want to have a local one. So global just meaning so what is the relationship between the features that you used and the output of your model. And the local one, if we actually want to narrow this down to a specific subset of our features, or even more if we want to actually understand why the certain prediction was made. So I think usual examples when this is useful are coming from the banking industries. For example, if someone is being denied a loan, usually you have to kind of give them a good reason for it. Talking about Booking, we have a couple of different, so we have a lot of machine learning use cases, starting from front end, so optimizing the website, but also some of the things that are happening behind the curtains. For example, we have quite a big fraud teams because fraud happens, unfortunately. We have, for example, so actually having an ability to get better understanding whether something is going to be a fraud, yes or no, gives us more power to act upon it. Also, sometimes we need to explain. For example, if the certain property is being forbidden of the joining on Booking.com because our model flagged it as this is a fraud property, we also need to be able to explain that. This also goes back to, for example, payment fraud, so all kinds of applications. But aside of those, let's say, classical explanations when we have to give an explanation to someone, also this gives us an opportunity to iterate on our products more, because getting better insights and understanding why certain predictions are made, how they're actually being made, can help us iterate the product better, or maybe even create a better model. So, how do we interpret the model? So, let's now go a step back, going into game theory. So let's say that we have a group of people that are playing a game, and the end of the result of how they play this game is a certain reward. So from the game, we can all assume that, let's say, the game is fair, and that's what we want to agree on. There's some rules, and that's that we want to distribute this reward towards these people. So we want to agree on certain rules. So these rules seem very straightforward, but they're actually quite powerful. So what we want to say is that the sum of what everyone receives should be equal to the total reward. So if the reward is 10, then what everyone got must sum up to 10. If two people contributed the same value, then they should receive the same amount for the reward. If someone contributed nothing, they get nothing. And if the group plays 2 games, then the individual reward from 2 separate games must sum up to the total reward of these 2 games. Sounds reasonable? Yes. So why am I mentioning this? Because what we're going to actually use is the Shapley values, which are originating from the classical game theory, and we can actually apply the same rules for the machine learning interpretability. When we think about the features and actually they're playing a game trying to get the prediction out. So for that, we're going to introduce a little bit of more math. So introducing the additive feature attribution methods, it's way more simpler than it looks like. So when we think about the model itself, we want to find an explanation of why our model is giving certain predictions. For simple models, well, model itself is already an explanation. That is trying to describe what is happening. For example, linear models, that is already straightforward. That's probably the reason why these models are being used so much, because they are so human-friendly. So they're readable, they're understandable. It's very easy to explain it to someone who is not into any kind of math. It's very easy to pinpoint why something happened. But when it comes to the ensemble methods, or even if it comes to the deep learning, that is not straightforward. It's not easy to understand, to describe why certain things are being produced. So what we want to do now is we actually want to, for this very complex models, we want to fit something simpler that is going to be an approximation, that is going to give us explanation of our predictions. So basically, with the additive feature attribution methods, we have an explanation model that is just a linear function of binary variables. So we have the simplified inputs of our features, and we have the linear combination of them. This is actually followed by three very nice properties, which are the local accuracy, missingness, and consistency. And I'm going to go through all three of them. And they're actually yielding something very powerful, but I'm not going to reveal it yet. So the first thing is the local accuracy. Again, it looks very scary, but basically it's just making sure that whatever the approximation model is giving back should be approximate to the general model. We shouldn't differ in that sense. The second thing being the missingness, which is that if the feature is missing, then it's attributing to no value. Going back to the rules of the game of theory, pretty much if someone did nothing, they get nothing. And the third one, consistency, so basically state that if a model changes, so that the simplified inputs contribution increases or stays the same, regardless of the other inputs, then the inputs attribution should not decrease. So out of these properties, we have a very powerful statement that there's only one possible explanation model that is satisfying these three properties and is following from this definition. So this actually implies that only methods based on the Shapley values are good enough to use as an explanation methods, and that all the other methods are going to violate local accuracy or consistency. So this funky formula in the middle, it's actually the Shapley values. So looks very scary, but basically what the Shapley values is trying to calculate so we're trying to calculate the importance of a certain feature by what happens when we include this feature minus what happens when we exclude this feature. So it's very straightforward. The big part about this previous statement is that it's actually claiming that this is the only method. So this is not just one more method to use in explanation and interpretability, but it's actually the only method. So any other method that is not based on this is going to violate some of the properties. And those are actually quite good properties that we want to have. So going back to the three methods, so variable importance plots are probably used every single day and everywhere. They're quite useful, they're quite insightful. However, they are actually violating the inconsistency part. So we actually, based on this theorem, have a statement that the variable importance, the information gain, is actually not consistent. So information gain has been used since 80s. It's very powerful. So basically what we're trying to do is understand the importance of the features when you look at the three methods, how much is contributing to so how often it's being used and how high up. So if you look at this example here, you can see that what can happen is that with the feature importance, the classical variable importance used in three methods, that the feature that is actually has the highest Shapley value is being attributed lower when you look at your feature variable importance graph than it actually should be. Why is this happening? For example, if you have features that are very highly correlated, then what can happen is that they get shifted, and then the actual Shapley values would not correspond to their actual attribution, what their actual attribution should be for the graph. So the Shapley values are quite powerful, and we're start using it now. So there is an implementation in H2O, so that's great. So we're start using it more and more within booking, because it gives us quite a lot of opportunity to get better indication for what is happening. One example is, for example, when we're predicting if someone is going to cancel a reservation, understanding what's happening behind, what are the mechanisms, help us to improve the processes further. Yeah, thank you.
We still have time for a few more questions. So if you have any question for Ivana, I bet she will be able to answer them.
No questions, okay.
Maybe I have one.
Yeah.
Can you maybe
Microphone is. Hold. Oh, Ross will tell me.
Hi, thanks a lot for a very interesting talk. I wonder if you could give it a bit more information or disclose how you use the many parameters of the target encoding transform. Like you mentioned that it's okay. Well, I think it's pointless at this point. But so my question is that you mentioned that you use some sort of Bayesian approach.
Yeah.
So do you impose a prior to those hyperparameters, and so what? And then what if it's some kind of Bayesian optimization framework, or do you use just a Bayesian estimation?
I don't know the details about it. I'm not the one behind it, but we have this B-Vizier. I think it's also, there's some of it that is open source, which is doing the Bayesian optimization of the hyperparameters.
Okay,
I
so
can
you
link.
basically run a Bayesian optimization.
Yeah.
Okay.
Great.
Okay.
Thank you.
Hi everyone, can you hear me? Oh, perfect. So, hi everyone, my name is Martin, and I will talk a little about enhancing Spark Pipeline API with sparkling water. We had the chance to already see part of it in the previous presentation. So let's get to it. First of all, what is Apache Spark? That's what we are trying to enhance. So Apache Spark is an analytics engine for large-scale data processing. It runs in like distributed clusters. It can transform a lot of data, and it's very often used in companies that have to deal with large data, and it's open source. So, and then what is H2O.ai? So H2O.ai is our implementation. It's also open source, and it's a distributed in-memory machine learning platform. So what does that mean? That means it's a group of algorithms that you can use that scale well, and then once you train them, you can export and get some trained artifacts called mojos, and you can use them for serving. And then we also have a project called Sparkling Water, which Kuba here and Marek are now responsible for, and that's a project that integrates H2O.ai algorithms to Apache Spark so that you can use them seamlessly. Sorry. Okay, so we already had a chance to see how Spark Pipeline API looks like. So you have two main components. One of them are transformers, and they have a function called transform. Basically, what they do is that they transform one data set or one data frame into another data frame, and those are classes like, for example, tokenizer, bucketizer, and so on, element-wise product. Then we have estimators. So estimators are objects that implement method fit, and basically before they can transform anything, they need to get some kind of information about the data. So they need to be fitted. And so they have this fit function, which accepts a data frame. It does some kind of aggregation, learning, whatever, with the data frame, and then creates a new transformer which it returns. And the typical examples are PCA, standard scalar, because you need to store the mean and variance, linear regression, random forest, and so on. And now the pipeline is similar. So Spark Pipeline is similar to Scikit-learn pipeline, if you're familiar with it, where you can chain different transformers and estimators, but here you can also chain multiple estimators with multiple transformers to create a machine learning workflow. And so the pipeline itself is an estimator. So first you need to call fit on it, and that returns a transformer. And so what are some sparkling water algorithms that you could use with this Spark Pipeline API? First of all, those would be generalized linear models, with which you can achieve something like linear regression, logistic regression, Poisson regression, different types of regressions. Then we also have deep learning, which in our case is mostly feed-forward neural nets. Then mainly what also people often use are gradient boosting machines, which are gradient boosted trees, XGBoost, distributed random forest. So these are ensemble methods that they bind or combine the predictions of weak learners, which are decision trees, to create better predictions. And then we also have something called AutoML. We will talk about it more, but what it basically does is that it combines all the models and then does stacking. And we will talk about stacking as well. So let's first have a look at how Spark Pipeline API can look like. I guess you can't see anything. All right, this should be big enough. So here we create something called evaluator first, which is able to evaluate the metric or quality of your predictions. And then we simply import class called, for example, H2O from PySparkling, which is our sparkling water implementation. And from PySpark, we can import pipeline and SQL transformer. We can chain it nicely in this pipeline here, where we have a pipe. We call fit on it, we get the transformer that's already fitted, and we can use it for predictions. So now here I chained two bits. One of them is H2O that's the predictor. And then I also chained SQL transformer, which just renames the output. And we will see here why. Because the original prediction came as a nested object, but we unnested it. And we can see how well we did on our validation data set. So this is what Spark Pipeline API looks like. Now let's talk about validation. So validation is something that a lot of us has to do often to assess the quality of our model. So how can you do it? Well, the first approach would be to create a random or stratified, but let's talk about random train validation test split. When you have your original data and you split it into three parts, train, validation, and test. Now, the train and validation, you can use that multiple times. You use it to iterate on your ideas, on your machine learning pipelines, on your algorithms, you try different hyperparameters. And the way you do it is you train your model on the train set and validate it on the validation set. And then once you're happy with the pipeline that you have, you can test it on the test set, but you run it on the test set only once. And why would you do that? Well, first of all, you most likely have already slightly overfitted to the validation set because you used it multiple times. And you want to see how well your model does generalize. So then there's something called cross-validation, which is a version of validation where you have only train and test split, and it's slightly more robust. Well, it is more robust. And the way it works is that you split your trained data set into multiple faults. And then for each fault, iteratively, you create a model, leaving that fault out. So the first fault would be left out here. We would train the data on, or train the model on the 4 faults here. And then we would validate on this data part of the data as our validation. And this way we would loop over all the faults to get a sense of evaluation of how well our model works. And again, we can repeat this many times. And as soon as we are happy with our hyperparameters in pipeline, we can test it on the test set. And so why am I talking about this? Well, let's talk about grid search. So what is a grid search? In previous presentation, you heard about hyperparameter tuning, which is basically you are trying to find the best set of hyperparameters, which are parameters of the algorithms you're using that are not trained during the fitting. So for example, that can be the depth of the tree, number of trees in the gradient boosted machine, it can be the learning rate, it can be penalization, type of penalization you're using. It could be a lot of stuff depending on different algorithms. And so the most basic way how to do it is to do a basic grid search. So for each hyperparameter, you specify a set of values it can have, and you create a grid, and this Cartesian grid, so every combination can be tried. Now the problem with this is that as soon as you have many hyperparameters, this space is extremely large, and it's hard to explore all of it. So instead, what you can do is you can do random grid search, which I'm sure many of you are familiar with, and that's when you don't fix the hyperparameters, but you can try out different combinations. So why am I talking about this? Well, Apache Spark only allows you to do the Cartesian grid search, and you can do it with the cross-validation or the train validation split, and it has two classes for that. While Sparkling Water allows you to do both random and traditional Cartesian grid search. And what Sparkling Water also allows you to do is to limit the execution time by, for example, number of models, the runtime, or some stopping criterion. So let's say you can say, stop the grid search as soon as the AUC didn't improve in 5 consecutive iterations by more than 0.05, for example. And now let's see how you can achieve this in Spark. So to do this in Spark using Sparkling Water, all you need to do again is import grid search and H2O algorithm that you want to choose. And now you have to specify your grid and say that you're not interested in Cartesian grid search, but instead you want to try random discrete grid search. And you can specify the number of models that you are willing to that you want to train, or you can specify maximum runtime, and you can limit it by different ways. And so you also have the ability to change if you want to perform cross-validation or the train validation split. So for cross-validation, you set the ratio to 1, which is the default, and number of faults to some number of faults. So that would be the number of these faults. Sorry. And if you wanted to do train validation split, you would just set faults to 0 and set ratio to the ratio of the train set. So if this was 0.8, it would mean that 80% of the data was used for training. And now when you have this grid search, you can have a look at your models and their performance. And you can also have a look at which hyperparameters were the best, right? Because that's what's most interesting. And maybe these hyperparameters can tell you something about the nature of your problem that you're dealing with. And you can all do this in Sparkling Water quite easily. And so now let's talk about stacking. So what stacking is? So gradient boosted trees are an ensembles of weak learners, while stacking is a form of ensembling strong learners. So you have your base algorithms or base trained models like GLMs, let's say, and gradient boosting machines, and then you have, and these all make predictions, and you take those predictions, feed them inside another model, and that gives you the final output. And now how do we do it in H2O, right? So you have your base learners with their hyperparameters. For each of the model, we do k-fault cross-validation when you can specify the fault. For each of the fault, we leave that fault out. We then use the rest for the training, and we generate a model. So for each fault, we have here one model, and we will use this model to make prediction for the fault that was left out. And we call it out-of-fault prediction. So we will use this. We will do this for all faults, and we have out-of-fault predictions for all the data. Then we do one more step, and that's it, that we train different models. So we have altogether k+1 models, and the last model is trained using all the data. Now, if we do this with each of the models and each of the hyperparameters, we get the out-of-fault predictions, which then we can create a matrix out of them in a way that we stack them. So you can see it here, clearly here. And so we have this new matrix of our out-of-fault predictions and our original target. Now we feed this inside the meta model that we selected. This could be, most often, is some kind of linear blender. So for example, linear regression with some penalization. and we get a new model, right? And so what will this model actually combine are these models that were trained using all the data, even though they were trained on the data that comes out of the cross-validated models. And that's to ensure that the models generalize as well. Okay, so let's have a look at how it would look like in prediction. So we have our base models. They make the base predictions. We stack the predictions together. We feed them into the meta model, and that gives us our final prediction. And now let's talk about H2O AutoML. So why did we talk about stacking? Well, so it turns out that H2O AutoML is nothing more than a set of base learners that you train in the cross-validated fashion as we discussed. For each of the fold, you get your model, create your out-of-fold prediction, and create the model using all the training data. So this we do for every model that we have, and then we create 2 stacked ensembles. It's always 2, as long as there's at least one class of algorithms that has models of 2 hyperparameters. So the first stacked ensemble is a stacked ensemble of the best algorithms of a family. So here we can see that, let's say the GBM2 scored AUC of 0.48, and so on. And so we stack only the best of the family. So GBM2 has AUC of 0.48. GLM1 has AUC of 0.79, which is worse than GBM1, but we still use this because it's a different family. So we create this stacked ensemble, and it can give us, let's say, AUC of 0.5. And then we do the same thing with all the models. And so this is what AutoML basically does. It creates base learners, stacks them, and then creates a leaderboard on the data that was held out, not used any time during the training, to establish some kind of order or rank. Now, let's have a look at it. How does it look like in code? So again, we only import H2O AutoML. We do the same thing as before. We create a pipeline with the rename stage, and we fit it. Okay, so we fitted our model, and we can see the leaderboard. And in the leaderboard, what most often happens is that the stacked ensemble of all the models performs the best. Here we used RMSE, so the lower the score, the better the model. Then the second best model is stacked ensemble, stacking the best models of each family. And then we can see the base model, how they performed. And so here you can achieve this in Spark with sparkling water very easily. You just import one class. You can say, this is the maximum runtime in seconds. I am able to wait, or I want to wait. You can specify which families of algorithms you want to use, which you want to exclude, how many models you want to wait for. And so it's similar as to grid search. You can select stopping criterion. And that's about it. So if you have any questions, and one last thing, you can always do the same thing with already trained H2O models. So if you have a model from H2O3 or driverless AI, you can always import it into Spark Pipeline API as well. So thank you for your attention. I'll wait if there's any questions.
Does it work?
Yes. Hello, Martin. Thank you for the presentation. You have shown the grid search. Is this grid search able also some kind of more sophisticated strategies? The SG boost, when the trees are too small, you don't have to be worried over overfitting, so you don't have to fiddle with the parameters limiting overfitting.
So
or if it's only random one.
This one is only random grid search, so it's random. The AutoML is different. I mean, it also has random grid search, I believe, but there are also a set of hyperparameters or combinations of hyperparameters that were shown to work well. So in AutoML, we start with a set of hyperparameters that are supposed to be quite okay, and then we do the grid search, if there's still enough time. I hope that answers your question.
Thank you.
Thank you for staying with us. In my today's presentation, I would like to tell you something about the machine learning interpretability, and I'll be talking about that in the context of our H2O driverless AI product. I'll be talking about that in, I would say, a broader way that Ivana did. So, I'm Martin Dvořák. I'm a backend MLI project engineer, and I'm with H2O.ai for 7 months. So, first I would like to give you some introduction and somehow tell you something about the scope of this presentation and the context in which I will be talking. Then I would like to tell you something about why explainability matters and why it's important to take attention of that. And the next thing I would like to talk about is what's important when you are building or want to build an interpretable model, some human-centered low-risk model. And finally, I would like to explain how we are explaining machine learning models and describe our solution, which is part of the driverless AI. So, machine learning interpretability is the ability to explain or present machine learning models in understandable terms to humans. I will be talking about the models which work with the structured data mostly, so we don't do image, video, and sound. So not that much deep learning, for instance. So it will be mostly about the table data and supervised machine learning. Also, this solution is related to our AutoML driverless AI, as I mentioned, not that AutoML or open source product. And finally, the core of the presentation is that MLI module, which is part of the driverless. So this is a description of some typical steps you do when you build a model. And usually or often, that machine learning interpretability step, when you are trying to explain the model, is at the end of the process. But I would like to describe that in like more holistic way. So I would like to talk about what you need to do from the beginning of that process to the end to get some reasonable model at the end, so that you can avoid some surprises and you can get better model. Okay. So first, let me start with the motivation, with the problem statement. What is worth to be interested in machine learning interpretability? So first thing is slightly controversial topic, I would say, which is the difference between the types of the models. There seems to be some trade-off between the accuracy and the interpretability in the models, and how we are progressing in research, this is slightly changing. But anyway, usually we somehow distinguish white box models and black box models, which is given basically by the feature engineering methods you use and the algorithm types. So we are looking usually for some balance. And examples of these models is, for instance, like decision tree as some white box model, which is easy to interpret, or some deep neural network, which is difficult to explain, or regression as a white box model, or stack ensemble as a black box model. And this slide somehow describes that trade-off. So in case of linear models, usually get exact explanations because it's straightforward, right? For approximate models. In case of machine learning models, you often or sometimes get approximate explanations because it's much more difficult for more accurate models, for exact models. The next thing, and maybe there's one important thing, why I'm talking about the trade-off is, as it depends how much accuracy you really need, and sometimes you really want to balance that accuracy with the interpretability, because you need to know what that black box model actually is doing, because the accuracy without understanding what's happening there may be dangerous, and I'll be talking about that later. So next thing, which describes why it's important to take care of, to be interested in the interpretability, is multiplicity of good models. So if you have a well understood data set and you use linear model, you have one like global minimum. That's simple. In the case of machine learning models, you can see there are multiple local minimums, and you can get multiple models that have like same objective metrics, basically have same performance, but internally they might be working differently. They might use different features. They might be like using different feature engineering, and some of these are better in the way how they use the data. Others can be very problematic. So the way how to choose between these models is, for instance, the machine learning interpretability, which will help you to understand these models. Next thing is the fairness and the social aspect. So you probably don't want to build a model that will have such problems. So it will be in some way discriminatory. So you don't want to make some decision based on gender, age, ethnicity, health, or sexual behavior. So that's very important. So this is where interpretability or the way, so the ability to explain the model may help. Another motivation is the trust in the model, both by the producers, consumers, and until consumers. So that's the difference between like the data set, that the way when you build the model, which is that green rectangle, and the red one, which is the real world. So we need to find out how your model will perform in a wild, right? So we need to make some introspection, look at out of range values, so you don't, get some, problematic predictions. Next thing is the security and hacking. So there are people who don't have good intentions, and they may want to compromise your model integrity. And there are different attack types, but basically one of them is, for instance, they try to build a surrogate model. I will be talking about these models later, to identify the vulnerabilities, to understand how your model works and where are the problems. And basically they do MLI on behalf of you or instead of you to find some problematic parts of your model, to identify some adversarial instances, and to sneak into something and to basically let the model classify something wrongly. So there might be like integrity problems or availability problems where false negative or false positive instances may really cause passing some check, which for instances that shouldn't pass that check, or they can block like legitimate access to other instances. And the next thing is anybody who is working in a regulated or controlled environment needs to, somehow explain how that model works because of the legal requirements just also mentioned by Ivana. So if you are working in banking, insurance, healthcare, you must explain your prediction and justify that, and explain one, for instance, you didn't get a loan or credit card. And there are other restrictions, so your model should be fair, must be secure, and in this environment usually it's interpretability over accuracy often. And so that's why here is simply the must to understand the model. And this is like a summary of what I just said. So you need to explain the methods because you need to balance the performance and interpretability and the other things that I was talking about. So now what's needed, what you can do, what you should do when you are building that model from the beginning to the end. So I'll be talking about some big picture and to-end story that we have, and I will be talking about it in the driverless AI context. And I will go step by step of the process or the possible process of building the model and what you can do to build that model and make it interpretable. So first you load the data and you do some explanatory data analysis and visualization. And this is actually a screenshot from our product. So this is the basic analysis, so you can see really basic information about the data set. And you want to also do some visualization to find out some interesting facts about your data set. So this is Autovis, and it's the similar module as the MLI. So in that case, you can be interested in some correlation graph of your features in outliers and many other evaluations that we have. You want to do that in order to find out and understand the model, to, for instance, be able to constrain some algorithms later to get more interpretable model, to find out some problems that might be part of your data. The first step is that feature engineering, as was mentioned. This is again the screenshot from our product, where we basically have three knobs, how you can control that auto ML. First is accuracy, the second is time, and third one is interpretability. And based on that, which is, doesn't matter whether you do that manually or whether that some auto ML does that, you need to choose the transformation that are used very carefully so that you don't basically kill the interpretability early in the beginning, because there are some transformations that can really complicate that later. And I have some examples of not that much interpretable feature here at the bottom. And you can see that here is the list of the transformations that are allowed in this case. And here is like the opposite situation when the interpretability is high. So we want to get some interpretable model, and as you can see, there is much less transformations which are allowed. And similarly, you do that for the models. So as I said, this is slightly controversial, but usually, in this graph there is accuracy, here is interpretability. You have some linear models. Here is bagging, boosting. Here is deep learning. We would like to have such model, right? It would be great, but that's pretty difficult. So this is again some balancing of the black box and white box models. So in our product, again, you can control that, and based on that interpretability setting, AutoNudge makes the choice of that model. And obviously you can go for some GLM models or some GBM models with some restriction, like monolithic restrictions, to make that balance, suitable for you. This is summary of what that knob controls in the product. So at the top is like that black box model. At the bottom there is a white box. So you can control that knob basically controls the ensemble level target transformations that are allowed, feature engineering transformations, monotonicity constraints, and other things. So basically with 10 you get some interpretable model, and here you get something more accurate but much less interpretable. You can even enforce the models that can be used, like here is an example of the GLM or like GPM model. I just put it there in expert settings. Now, so once you get the model, this is end of some experiment. You should check your model what was built. So you check like AUC and other metrics, and you can look at the confusion matrix and to find out what you actually built. We also provide the experiment summary, which describe that model that autonomous solution built, so you can check what actually happened, which transformation were used, whether it's okay, which algorithm were used, how that ensemble was built, for instance, to really find out whether you are getting what you want to get. And you do some kind of a diagnostics, so you can upload the data set and let that model to do the predictions and get, again, some objective metrics, get confusion matrix, for instance. You can do with this, you could in principle do things like despite impact analysis, for instance. In next stage, what you should do is that post-hoc like steps. So check, do some debugging. So do what if analysis, sensitivity analysis, which can give you some self-confidence about how that model works out of that data set you provided. You can try to get reason codes to find out how the model does the decisions and solve that bias assessment and remediate it, with the despite impact analysis. So finally, there is a step which is like you can be seen as a human review of these steps, and this is where you can run that MLI plugin, that part of the driverless that we're talking about. And I would like to somehow say that the human review is really important, because as a human you understand the semantics of the features, you know what's important, what makes sense, what doesn't make sense, and certain things simply machines cannot do. You really understand the data. So this is a dashboard of that MLI plugin I'll be talking about. And this process is iterative, as was mentioned. So usually you do it until you get the desired model with the desired features. So now let me do a deep dive into our MLI solution. So as I said, after that experiment ends, you can switch to that. What we do in our MLI solution, we have some explanation solution both for the standard models and also for time series models, where we showing you both of these things. And the typical walkthrough how you do that is that first you are interested in some global approximate model behavior. Then you look for the feature importance, and we have a couple of methods that we use. Once you find out which are the most important features, you are interested about their behavior, how they interact with the prediction. Then once you know this global behavior, you may be interested in some specific instances that might be like suspicious, problematic, or there may be some extreme values. And you want to make a reason codes to find out how they were, why that the prediction and which features contributed and how to the prediction. And that's the way how you can get from the global view to the local view. So then you can, somehow find out how that model behaves in that local case, and how in that for particular instances how the prediction was made, which features were important in that particular instance, and finally how they interacted and how they behave. And all these things are, you do for that model to find out and understand what's happening there and to pinpoint the problematic parts. So as we'll be showing the demo, I have some data set, which is a credit card data set. What that data set does is that there are features, and what we will be trying to predict whether some bank customer will default next month or not. And the features which are in the data set is limit balance, gender, education, marriage. And there are important features like pay 1 to pay 6, which are categorical features, and they value means that if there is -1, it means that they paid you late, and if there is 1, it means that the customer didn't pay last month, and if there is 2, he didn't pay for 2 months, etc., up to 8. And as I said, we'll be predicting this value. So let me now switch to the product. So this is finished. There are some finished experiments. So I can open that credit card experiment. Okay. And as I said, here you can see the screen I was showing earlier, and you can choose to interpret the model. So I pre-computed this stuff. And the home page show how these explanations are connected to that original experiment. And this is the dashboard, which shows at the beginning the global view. And the bottom left corner, we built a decision tree that shows really approximate behavior of that model. And as you can see in the root of that decision tree, there is a pay1 property feature. And that feature means how that whether that customer paid in the recent month. And here is a global view of that model and feature importance. And again, pay1 is at the top there. So I know which are the most important features. And for these most important features, I can investigate how they behave, how they interact with the prediction. So we build a partial dependence plot and show the interaction. So that's the main view. So now now let me explain how these things are done. Okay, so So earlier I was talking that basically that the models that can be built are either white box or black box models. So in case of the black box models, it's difficult to find out how they work internally because there is no introspection and it's difficult to understand how they work internally. So what we use to be able to explain this model, we use surrogate models. And by these surrogate models are built as follows. The surrogate model is built on predictions of that original model. So at the top here is the experiment from that AutoML. So as the data, here are the labels, and you build the model, you get the model, and then you take these predictions and you build another model. And this yellow one is a surrogate model. And in this case, this yellow model is some white box model. So for instance, we train on this prediction of that original model, decision tree, or GLM on other model that is easy to interpret. And also for this model, we know his objective statistics, so we know how much we are off and whether these explanations, how we can trust them basically, how much you can trust them when you are looking at these explanations. So in case of that feature importance, for instance, we built random forest, which has some introspection based on how the features split the space. We use that introspection to find out which are the important features. As you can see, this is done on the original features, so you really find out what's happening there. But still, there might be some error. Another method is that in some cases you can do the introspection and that model can tell you what's happening inside, but in that case we simply have there like transform features, not the original one. And both these methods are, for instance, faster than other things. And now I'm getting to the third method that Imana mentioned before, which are Shipley values. So we use Shipley values to do that feature importance to compute it, and we do that on transform features again because that's the way how we can get it from the model. This is some explanation. I don't want to repeat that much, but basically that analogy was already mentioned, that you want to get that Shipley value which explains the contribution of the feature for the particle in case of the particular instance. So you have an instance, and that instance you can see it as a game. Features are players, and the prediction is some game. And when to find out how the players, which are the features, contributed there, and how you do that, what we basically do, you should compute all the coalitions and find out the contributions there, and then average them. So that's how it's done. It's the method from 50s, as was mentioned, was a game theory thing. The problem is that that method has exponential time complexity. So usually what you use is some kind of approximation, and in that approximation you need to balance the accuracy and the time you have. That's important to say. And if you would do that as expected, there is a guarantee that you get really fair distribution among all the features, and therefore Shipley values is the most reliable and basically the only way how you can reliably find out the feature importance. And apart to that, we also have loco, which is leave one coordinate out, which completes these feature importance methods, the other importance methods, and it can explain how in global, normally still talking about global importance, how in global these features contribute where basically the tendency of the bias in these features. And the loco is computed by leaving one of the features out, right? So what you do the prediction, then you leave one feature out, and do the prediction and do the subtraction. So this is how it's computed. So this is like summary of the methods we use. And basically there is a trade-off between them. Some of them has some error once they are on a surrogate model, but you always know that error, how big it is. Or you can use like Shipley values, but in that case it might be more problematic to compute. And also there is a difference between original and transformed features. So once you know the important features, I said, so we compute partial dependence plot, and in this case you want to find out whether there is some interaction of that feature and the prediction. So again, it's computed by default on the PDP on the surrogate model, and how it's computed is described in here. What you do, you take the data set, and for instance, in case of that pay1 feature, which is categorical, you fix the value for all the values. So there were values between -1 and 8, so you fix it to -1, you do all the predictions, and do average them. And here you can see that there is probably some interaction. So what it says, how you read this type of the chart, is that if it looks like this, there is no interaction, this would be like linear interaction, and here would be like some interaction, because it is simply changing. Okay. Next thing, as I said, once you know this global behavior, you may be interested in certain things that are suspicious or problematic, and in that case, you basically go from the global view to the local one. So I can choose, in this case, from this chart, some example. I can see the reason code, and if I click on that example, I am zoomed in to some more detailed view, and also what I get is some local view for that particular instance. So this is the particular example. I can see how it would be probably classified using that tree. Here I can see how features are important in this particular case, so for instance DB switch. And here I can see these yellow dots, these gray dots, that these values, how it interacts with the prediction. This yellow dotted line is the original prediction of that original model. So. And if I want to get the explanations, I can go just here and I get the explanations for this. So here are the reason codes. So as you can see, the pay1, 0, the most important one, contributed most. And so here I have a list of features that contributed positively to the prediction that that customer will default. And here are the features that contributed negatively. So now let me explain how we computed. As I said, this drill down is a transition from the global to local scope, and again, because there is a problem with these black box models, we use a surrogate model, a K-Lime surrogate model. And what the K-Lime is, so Lime is local interpretable model agnostic explanation, and that's method that works, as follows. You choose some set of some explanatory examples. In this case, it is binary classification, so there is that yellow color and that black color. So, you choose some examples, and you predict them using the original model. And you also weight them based on the distance from the instance you want to explain, which is that orange cross. And once you have these examples and you know the weights, you train the model, like this line, like a regression line, and you get some linear model. And then you can explain, by casting in the data, how that in this local scope, how that works basically. What is happening there and what's most probably happening there. So you are basically some complex thing trying to approximate locally in some region. In order to make it more precise, you don't do it on global, but we clustered it first. So we do k-means clustering, and then within these clusters we do the Lime to get better results. So that was the zoom when I clicked from the global view to some local line and took me to the cluster, which you can see in here. Here is that cluster as I zoom in, and here are the explanation I was talking about. And this gives us this reason code. The reason code is a multiplication of the coefficient of that linear model and the particular value for that instance. This was that local approximate behavior. Again, we just went through the decision tree to find out how probably that instance would be classified. We have that local feature importance, and here we use the same methods basically. And finally, here is that local feature behavior, which is computed using eyes. And eyes are individual conditional expectations, and it's computed in similar way how the BDP is. What you do, you choose that particular instance and you fix the value for that feature, for instance for pay1, for all its values, and then you track the interaction. So these are the yellow colors. So I put into that line, I set it to -1, do prediction, 1, do prediction, etc. And this is how I get this chart. And it shows me whether there is some interaction in this particular case and what's the type of that interaction. You can get, apart of this interactive UI, you can get a report which we call Autodoc, which contains computed some of the interesting things and facts about that model. So for instance, it can compute that PDP for out-of-range values, which go outside of the range of the features within your data set to find out whether there is a problem or not. And also you have more information about that in this comprehensive form. So as I said, apart to what I just was presenting, we also try to explain also time series experiments. In this case, let me just switch to the list of experiments I have in here. And open again, this is the finished experiment for the time series. And I specified the test data set. And as you specify that, what you can see is a global view of the predictions. We show you some groups that was identified within the data set, and if you provide the test data set for that forecast horizon, you can choose one of the groups and see the difference there, how it performs, and for particular predictions within that forecast horizon, I can get also Shapley values. So these are like Shapley values, local Shapley values for some particular time here, for a particular time in that forecast horizon. So that's the beginning of some initial implementation of the MLI for the time series. And that UI is structured so that you can compare different models, compare the groups, and find out how these models perform. So you can get information about that MLI plugin in our documentation. We have some comprehensive cheat sheet. There is also in the presentation will be description how exactly we do the surrogate models, how we do all these charts. You can see which methods we used and which metrics we used to find out how accurate they are. So that's basically what I wanted to present today, and I have just a few notes. So I've tried to explain why the interpretability matters, and you should remember that there is multiplicity of these good models, and you can choose between them based on the understanding how they work internally. H2O driverless AI has an interpretability as a part of the product, and with that you have some methods, plugins that you can use end-to-end in that process of building models. And you should test both your model and explanatory software to find out whether they work correctly. You should use the synergy of the local and global techniques. And finally, Shapley values is an important technique that we use, for instance, for feature importance, but this is also used in other contexts. Whenever you want to basically get some interpretable model, it's sometimes used to help you with that. And so this is the theme. And I would like to thank you for listening. Thank you.